Hi, good afternoon. Thanks for coming to our senior thesis presentation on design analysis and multi-objective optimization of winglets. I'm Abraham Neese.
I'm Shanae Powell.
I'm Sohail Reddy.
The pressure grade that's created on the wing during flight tends to equalize itself at the wing tip, creating vortices over here in this region. These vortices create additional induced drag on an aircraft. Winglets are one way to approach this challenge. Our focus is to optimize multi-winglets. Benefits of winglets are many. To namely, will reduce fuel consumption overall. For aircraft trailing in its wake, they'll experience less turbulence in that region. Also, engines can be operated at lower settings, thereby reducing fuel emissions and also noise pollution. Additionally, aircraft can achieve the takeoff velocity a lot quicker and a shorter distance, lowering the turnover time on the airports, on runways between aircraft. And now to our CAD.
Alright, so for our computer-aided design, to the left of your screen is a 3D rendering view of our split winglet, and it was created in SolidWorks. How we create our models is that we have Fortran code, which contains the 12 parameters that we're dealing with, namely the taper ratio, the tip twist angle, the trailing edge sweep, and the lame curves, which in itself has 3 additional parameters. So when we run our Fortran code, we import this geometry file into SolidWorks, which creates our new models.
Okay, our approach. As you know, we're controlling our winglets with 12 parameters, 12 variables. The 13th parameter is actually the airflow of the winglet itself, which is kept constant. We're using a PSU 90-125 airfoil, which was analyzed in XFOIL, a 2D code written by Professor Mark Drella at MIT. It showed, the CFD analysis showed that had very little laminar separation at high Reynolds number, which leads to less drag. It also showed that nowhere around this airfoil does the flow go transonic. This results in, this reduces shock-induced drag since we're not having shock wave. And now with the analysis?
Alright, so for the analysis, since we're dealing with fluid flow, we have to discretize our domain. So we meshed our geometry, which is the wing with the winglet, using 3D computational generation, and we did surface meshing, mainly because we're dealing with fluid flow on the external surface. We did a near model approach, near surface model approach, mainly because we want to find out what the boundary phenomena is like, and effective meshing leads to accurate results at low computational cost.
Computational fluid dynamics, CFD for short. We'll be carrying out our CFD computations in ANSYS Fluent, which is a finite volume solver. This will solve the governing non-Stokes equation, the conservation of mass, linear momentum, and the energy conservation. We'll be using a density-based solver. Because we're operating at a high Mach number of 0.8, we're expecting compressible flow. So this density-based iteration scheme takes that density change into account. We'll be using a shear stress transport turbulence model to model the flow separation and vortices at the wing tips. Our multi-objective optimization, the main goal of this project, we'll be using a response surface approximation method in a software called Mode Frontier. We'll have 12 input variables, basically our 12 parameters for the winglet, and we'll have 2 objectives, coefficient of lift and drag, 2 objective functions. The simultaneous objective is maximization of lift and minimization of drag. This response surface will be created using radial basis function, and it will be searched by a genetic algorithm, which would give us many virtual Pareto designs. We'll choose a Pareto optimum shape that fits our criteria. We'll validate this design through CFD and through experimental testing. And now the global component.
Alright, so aircrafts are used everywhere, and it's a global phenomenon. And for the manufacturing of winglets, Airbus in France has already manufactured and used the winglets, as well as Boeing in the United States. Also for the global impact, winglets reduce, it causes less fuel to be burned, and when less fuel is burned, we have less air pollution. And for global engagement, we're involved with working with an engineer from Austria.
To conclude, benefits of winglets are many. To name a few, there will be a reduction in fuel consumption, an increase in payload, an increase in range, reduced takeoff distance. This is our timeline. We expect to finish by March. And our hours spent is a total of approximately 350 hours. And our approximate cost is around $1,100 at this time.
We'd like to acknowledge our mentor, our advisor, Professor George Bilikovic. Dr. Helmut Sobieski, who's in Austria, Vienna right now. He's been helping us a lot with geometry parameterization. He's an engineer. Abbas Abdulli, he's a PhD student in MedRat Laboratory. He's actually sitting back there. Thank you for coming. And SOK for providing us with Remote Frontier. And that concludes our presentation. Thank you.
Excellent presentation. I have two questions. Winglets are not new,
No.
so what's different about yours?
Okay, there are two types of, actually many types of winglets. That's one that the 2010 team did. They call blended winglets. There's one from Airbus, of wingtip fence, as you can see over here. What we're actually trying to do is to look at multi-winglets. A little part going up and part going down, to see how that would benefit. So that's a new concept that we're trying to
I see, so you'll have a piece of the winglet going down.
split, exactly.
Okay,
Split.
all right, I didn't get that.
Yeah.
All right, the other thing, you mentioned that maximum velocity was gonna be 0.8 Mach.
Yep.
Well, being a pilot, I know that sometimes there are emergency situations where you're probably gonna have to exceed that to try and get out of an emergency situation. In that case, if I'm in the compressible regime and I have to go over 0.8 Mach, we know about Mach tuck and all of that. Are you aware of that?
Not entirely.
Okay, well, remember that, Mach tuck. So I'm gonna ask the question, what are the consequences to the airplane under those operating circumstances?
So we are optimizing our winglets strictly for the cruise part, because the whole point of winglets is to reduce drag. So we know most of the fuel is burned during the cruise aspect of the flight. So our goal is to minimize.
Now, remember, my keyword was
Yeah,
emergency.
Exactly, emergency. We will take that into account. Right now, we're not looking at so much the structural part of it. So we are not considering the structural element to see how the winglets will affect, say, oscillation or so. So our goal is strictly aerodynamic optimization.
All right, bear in mind, Mach tuck, do some more research on that.
Definitely. Thank
They're
you
a
for
serious issue.
Thank you.
All right.
Yes.
I was pretty impressed with the experimental, or the analytical methods you used. The question I wanted to throw out is, how are you going to model it, and what outputs are you going to compare to your theoretical?
Okay.
We're gonna model it in, we started CAD and SolidWorks.
Experimentally model it.
Okay.
This has been rapid prototype. Okay, this was done by 2010 team. What we're going to do is, we know that induced drag is maximum at takeoff. Induced drag is directly proportional to lift squared. So we will run a separate CFD analysis at takeoff. And we will create a model, and we'll put that in the wind tunnel at Embry-Riddle University, and we'll validate that. And we will be validating our optimum parameter design, the final design that we get, and we'll compare that to simulation.
And you're going to measure,
We're gonna
what are
use a
the
force
output
balance.
parameters? Drag and lift?
Normal force, yeah. We'll drag it. We'll use a force balance for that. And we also want to visualize flow structure to see how the vortexes change. That'd be a very interesting to look at.
You stated in the report here, you said one of the goals of the project is to increase the efficiency of the blended winglets by 2%. Why 2%?
Well, we want to set our goals very clear to see what our minimum requirement should be. What the 2010 team did when they optimized it for a Boeing 757 is they set their benchmark as 2%. So we're expecting another 4%, you could say 4% from the initial without the winglets, and 2% from the blended winglets. That's what we're comparing it to. So it's just like a benchmark given from statistical data. That's the aviation partners, Boeing, they came out with scimitar winglets. So using their statistical data, we set our limits at around 2%. 2% is a huge change in terms of fuel consumption. It's really massive. Any more questions?
Any more questions?
Very good.